How's it going, Chicago Python community? My name is Ali Sivji. I am one of the organizers of the Chicago Python Users Group, and I will be your MC for today's main meeting. Thanks for joining us on this Thursday. I actually was outside and it was like snowing a little bit today in Chicago, so a little weird. All right, so today is our Dunder main meeting. We have these on the second Thursday of every single month. Before we do get started, I want to make everybody aware of our code of conduct. A lot of these things are going to be enforced in both our Slack workspace as well as our YouTube chat. So there's that on our website. Please take a look. So what is Chippy? So Chippy, or the Chicago Python Users Group, is a Python-focused community that was started back in 2003. It started off as a few folks that were meeting once a month in small conference rooms or in the back of a bar. And now it's grown to become one of the largest Python user groups in the world, with 4 to 6 events every single month. So some of our initiatives on top of our Dunder main meeting, we have a monthly project night, and there folks either bring their own project or we provide a challenge project that teams of 4 mob program on together. And at the end, we pick a group to go up and present. We're going to be trying to do this project next week, so keep an eye out. It's going to be a lot of fun. And we also have a mentorship program that's currently being changed up a little bit, so stay tuned. We'll have some updates in the coming weeks about that. So on top of all of these initiatives, we have special interest groups, and these are activities and events that focus in on more niche areas of Python. So we have a finance SIG. There's a special interest group for data. We have one for web dev / DevOps. That was actually one that we did on Thursday. That was our first ever Chippy YouTube stream. And we also have special interest groups on algorithms and coding interviews. I actually see T in the chat. So shout out to T for starting out both the project night as well as the algo SIG. It's a lot of those great initiatives. Can't do it without our community. So we do have some upcoming announcements. Next Thursday, which is going to be April 16th, we're going to be holding a virtual project night. So if you join us on Slack, we're going to be having like organizers in different rooms, and we're just going to try to work virtually as a community that way. There's more information on our meetup, so check that out. What other announcements? I guess next week is supposed to be PyCon, so that has been canceled, unfortunately. And Chippy, this event was going to be our PyCon preview night. Fortunately, we did get one of our speakers to give so we're going to be giving a talk, and that's going to be a talk that they're going to be giving virtually at PyCon next week. And our second speaker, they're also going to be speaking at PyCon, but the talk they're giving, it's going to be more. I think it's a new talk. It's going to be Simpson themed. Really excited about that. So these 2 talks are Learning About Service Uptime by Mason Egger and Homer Simpson, and then Dean Wampler talking about Ray, which is a framework for building distributed Python applications. So before we do get into the talks, I just want to provide us some information on how you can connect with Chippy. You can join our Slack workspace. We have close to 2,000 people there. So if you go to join chippyslack.herokuapp.com, you can send yourself an invite. We're also on the Twitter. Our handle is @ChicagoPython. We're always sharing information about what's going on in Chicago, as well as the wider Python ecosystem around the world. And all the things I've talked about and more are available on our website, and that is chippy.org. Also, since we are doing this meeting virtually, I just want to make everybody aware of how we're going to just be doing Q&A. So if you look to the right side over here, we're going to be having a window. Looks like a lot of you folks have actually already found the window and are having a conversation there. So if you just want to ask your questions during the talk, We do have a little bit of a delay. We'd like to just get them queued up so we can reduce the amount of dead air. We'll also have reminders scrolling on the bottom of the screen just to have everybody aware of what's going on. Also, as a discussion, hit up the comments, hit up the live chat. Tell me what your favorite Python library is. Is it requests? Is it PyTest? A lot of folks are into Python because of the data science ecosystem. So I think we're going to see a lot of answers like pandas and like scikit-learn. But you really didn't come here to hear me talk. We're actually going to be bringing Mason on. He's going to talk about service uptime. So I'm just going to get him on the stream. Hey, Mason, how's it going?
It's going well, Ollie. How are you doing?
I'm doing good. Can you just introduce yourself to our audience?
My name is Mason Egger. I am a developer advocate at DigitalOcean. I've been there roughly 6-ish months. On my Twitter and on my website, I claim that I'm a reformed SRE that turned developer advocate. I was a site reliability engineer for an Expedia Group company for a little while, and yeah.
Awesome. So how did you get into Python?
So my first job out of college actually was in Python. So we ended up my first job was actually with a company called ForcePoint, which is a Raytheon company that does cybersecurity products. And the team that I was on was the appliance team, and we ended up building out a custom operating system and its system and like basically physical platform appliance maintenance backend for the cybersecurity products that all were hosted on this appliance, and that entire project was in Python. So I learned Python in my first job. I attended my first PyCon, I think in 2017, while I was working there, and I've been going back ever since, and it's been great.
Awesome. Yeah, that's actually how we met. Always see you around at those regional conferences as well as the big ones like PyCon. But just as a developer advocate working at DigitalOcean and being somebody that goes to a lot of conferences, I just want to get you, what are your experiences right now? Like, what is going on with you personally as well as DigitalOcean and their COVID response?
Well, I joined, I had been doing conferences by myself for a while. The last year I kind of did this North American tour of like 6 different Python conferences between the United States and then one in Mexico, which was really awesome. Nothing better than Python on the beach. But I was doing it all myself, and I decided, hey, I'm already doing this. It's kind of something I want to do at least for a little while. Let me join an advocacy team and be paid to do this instead of me paying for it out of pocket. And I got to go to one conference this year before the shutdown. I got to go to Sunshine PHP in Miami, Florida, which actually wasn't bad. I actually really enjoyed. So really and truly, like, advocacy roles include travel and conference speaking, but it's actually not really a main focus. Like, it doesn't have to be. You can do advocacy and not go to conferences at all. There are some advocates that do that. Some of them focus on creating content. Some of them focus on maybe open source code or being more like involved in digital communities and stuff. So it's caused me to have to kind of change what my plans were for this year. Like with my, the plans you put into the thing that HR makes HR happy. And nobody looks at again. But I've had to change a little bit of it, but it's really not that bad. With DigitalOcean's COVID response has actually been pretty impressive, and I've been very happy with it. We've released the DigitalOcean, I think it's called Hub for Good, or I think that's what it's called, something around those lines. And it's a way where people who are working on COVID-19 response technologies and stuff, we have a couple journalists that have done it, a couple of people that are doing scientific research and stuff. You can apply for credits, and DigitalOcean will provide you with credits to back that project.
Oh, that's fantastic. It's good to see that I see a lot of great initiatives. Like, I know, especially in the data science community, a lot of folks have been making websites and just helping those folks on the front lines better make plans for how to react to what's going on. But I also see you got something going on behind you. What's going on behind you? Are you in Springfield by any chance?
No, I'm just bored and have to stay home. No, there was something, Facebook ads never get me, but one got me, and it was like $20 for this technology called XSplit VCam that basically does green screening it takes in your input and then creates a virtual output of like a virtual camera, and then you can use that in any sort of app that you want to use to do like green screen without a green screen. And Zoom already kind of does that, but we don't really use Zoom at DigitalOcean. We use Google Hangouts, and there wasn't a way to do that. And I was like, $20, let me try it. It works pretty well. And I do enough live streaming and stuff on Twitch to where I was kind of like, yeah, let's do it. So I was like, $20, it's worth it. And I've been really enjoying it. It makes meetings more fun. That's for sure.
Yeah, for sure. Like, I think it's the perfect background for your talk. Speaking of which, are you all queued up, ready to go?
Yes, I am ready to go.
Awesome. So Mason Egger, please take it away.
Definitely. Okay, so if you missed that first part, my name is Mason Egger, and I am a developer advocate for DigitalOcean. Feel free to follow me on Twitter at Mason Egger. If you end up having questions that I don't get to tonight, or you have a random question that pops up in your head, or if you think that there's a better Simpsons meme for the things that I've done, please let me know, because I literally spent all day writing this talk and getting the Simpsons memes, and some of them I'm like, yes, that's the perfect meme for that topic, and the rest of them I'm kind of like, So if you've got a better meme, would love to see them. Also, if you want to watch, if you're into Twitch and live coding and stuff, I do live code streams on Twitch at SLD'OHs Codes. I do these on Tuesdays afternoon, 3:30ish Central Time. So feel free to join me there. If you want, I also announce it when I'm on Twitter. So you're only going to follow me at one place. Okay. Come on, PowerPoint. There we go. So a couple of resources that I used for this talk. Most of this talk comes out of the Google SRE books or my personal experience. When I worked at Vrbo, which is VRBO, Vacation Rentals by Owner, they changed the name. It used to be called HomeAway. It's definitely owned by Expedia Group. I was a site reliability engineer for their cloud platform team. Vrbo has an internal pass that all applications are deployed onto, and I basically helped stand up a lot of that and build it out. So we read the Google SRE books while I was there, and at the same time, we had our own kind of methodologies that we sprinkled in. So it's a lot of Google SRE book with a lot of like anecdotal stuff from myself. Also, if you want to make Simpsons memes, Frankiac is a great website for that. So disclaimers. This talk is essentially a Simpsons meme with a few helpful tidbits here and there. I hope we get some useful stuff in here. I was kind of curious about how many Simpsons memes I could fit into a single presentation and slip it past organizers without them noticing. And it seems like I did. I managed to get it over. So we will definitely see how many there are. In my past job, back when I was doing my SRE work, whenever the clusters would go down or where we would have a problem, I typically would find myself sending my teammates some form of Simpsons GIF or meme to lighten the mood, because there's nothing fun when your production cluster goes down. It's actually a really tense time. So eventually I realized I could probably explain my entire job in memes, and that's always been a life goal of mine. And I even get to do it in Simpsons memes, which is even better. So hold on. I hope you're ready for a lot of Simpsons content and hopefully some useful content at the same time. But here we go. So all those disclaimers just make me want to do it more. So welcome to The Simpsons. This is Homer Simpson. He is a nuclear technician at the Springfield power plant. This is also sometimes me when I'm working at work, because I have a whirly chair and that's just fun to do. I maintain, just like he maintains the power plant, a lot of DevOps and site reliability engineers and just engineers in general maintain a lot of code base that runs in the wild and in production. But oh no, something's gone off. PagerDuty is upset, and now the website is going down and we have to fix it. And we go through all of these things and we figure out how to fix it and we get it going. And then, a couple people come in, that are really calm about it. And then there's the people that come in who are like, the world is falling and somebody please needs to think of the children because the website is down. So we go all through that and say we get the entire situation fixed. We now get dropped into a lovely root cause analysis meeting where eventually at some point, someone will say the phrase, hey, what are SREs and how can we utilize them? Man, I am really enjoying my memes. So the Google SRE book actually has what I consider one of the best definitions for a site reliability engineer. And I really like it, and I'm going to kind of paraphrase this. Essentially, a site reliability engineer is someone who is an engineer who specializes in the entire life cycle of software. So very often, I've seen in some software engineering jobs, and especially in some roles that I've seen, is the engineer will create the code, write the code, and then once it's released, it kind of gets thrown over the bus onto a QA or to a support team or into, some sort of nether that it never comes back from. Site reliability engineers, on the other hand, kind of focus in the entire life cycle. They focus in the deployment and the operation of it, the refinement, and then eventually peaceful decommissioning. This discipline uses a wide range of skills, but there is definitely some overlap with traditional software engineering. But there's definitely a lot of skills that are completely separate from software engineering that you really wouldn't see, say, in a university classroom or even like a boot camp or something. You really don't see these kind of principles being taught. So, and then someone will always say, "Hey, we need a site reliability engineer, or we need a team of them. We need DevOps, we need SRE, we need Kubernetes, we need some big fancy word that solves our problem." There's a great Dilbert comic about that where you just say, like, I think you're what it turns into. But in reality, well, SRE teams are great, and I came from one, so I can never disparage them. SRE teams are really good at very large companies that have big budgets and have large deployments and such. But if you're working at, say, a small startup or something, simple DevOps engineer or a sysadmin will do. But in reality, what you don't need the magic of the SRE. What you need is a way of being able to measure your uptime and guaranteeing availability for your users. It's trying to solve the problem with people instead of identifying the problem. So, what is uptime? Well, my service is running, then I can ping it. That means it's up, correct? It worked. It's a miracle. That's not really the truth, though, is it? If the service is up, but nobody can access it, is the service actually up? Is it useful? If nobody can use it, then does it actually serve its purpose? If a tree falls in the forest and nobody hears it, did it fall and all that? So in reality, uptime is useful. And I used to know a lot of sysadmin friends that loved going in and being like, they would type uptime on their Linux machine and they'd be like, look, this server's been up for 10 years. And, that's pretty dope and it could be pretty awesome. But, if it wasn't available for some certain amount of times, that really doesn't matter. So in reality, we don't really care so much about uptime per se. What we care about is availability. So how do we measure availability? There's actually a couple of ways to do it. We can do it through time-based availability, which is essentially an uptime-based availability. This is where basically the availability becomes your uptime over your uptime plus your downtime, which is essentially uptime over the entire time. It's some services actually can get away with this. Like if you have a low-impact service or it's a really simple service that doesn't have like 600 micro services going, maybe you have a single website or a single Flask or Django app that's running, maybe this kind of uptime works for you. And in reality, at the end of the day, what this entire presentation is about doing what's best for you and what gets you the results you need to get. But we also have aggregate availability, which is where we have the availability of the total requests, for instance, or the successful requests over the total requests. This is actually a little bit more useful because this is also could be negated to use for unsuccessful requests, and the error rate, which could be turned to the error rate. But where this is useful is, like, if you have a highly distributed system. So imagine Google. Google. If Google just went with time-based availability, that really wouldn't be that useful for them, because with highly distributed systems, there's a likelihood that some subset of all of the services are running on some part of the earth. So if Gmail is down for all of North America, but it's up for Europe, technically the uptime on it's still up because it's being measured and is the service up. Whereas where it's aggregate availability, maybe what you do is you start to see how many people are getting either 400 or 500 HTTP requests. And as you breach this threshold, you start to see, hey, we're up above a certain amount. Maybe this leads to an outage, or maybe this is the smoking gun that we actually currently have an outage. So doing successful requests over total request is one example of many different ways of doing it. But one thing about it is not all requests are created equal. So aggregate availability, again, is really useful. But it says is in complex systems, not all of your requests are created equal. A new user sign up page or a sign up request may be different from like a message send request. If Gmail were to go down and people couldn't sign up, per se, that's irritating, but that's not, as bad as if nobody could send emails through Gmail. That one is, slightly, I guess, worse. I was going to say slightly more better, but that's not even a real phrase and not even correct. It's slightly worse than people not being able to sign up, because the day-to-day operations could still move forward. Another thing that you have to ask yourself whenever you're figuring out about which requests you need to monitor and which requests you don't is, do different types of failures have different effects? Same thing with the Gmail example. People not being able to sign up, the likelihood is that people are, if I can't sign up for an email service like Gmail or something's up, I'll probably be like, you know what, I'll come back later. Maybe the website's a little bit, maybe I'll go, grab a cup of water or something, come back. I'll come back later. Whereas if I can't send emails and that kind of outage persists for a long period of time, is if you can't send those emails, that actually might cause to, loss of customers, people being displeased with the service, going on Twitter and putting you on blast. Or just, anything more. It could potentially be a lot worse. So in my mind, I would say that that's probably a much more valuable request to track, and we should track that one probably higher than we track the, new user sign up thing. What other service metrics are important to take into account? These are other things that you have to ask yourself. So things like HTTP response rates, latency within, if it takes a long time for that message to process because maybe it's taking a long time to get through the outbound mail servers, you need to take a look into that. So how services interconnect and talk with each other. If the latency between these three microservices that run becomes really big in one area, maybe you want to know what's going on with that and see that. So defining availability. How do we know if we're available enough? Here's Grandpa Simpson out in the cold and there's wolves after him. How do we know if we're actually available enough? What level of service do your users expect? Are you the kind of service that if I can't send an email right this second, but I can send it in 5 minutes, is that really that big of a deal? Or maybe I'm it was a random idea that I was thinking of the other day. Maybe I'm a website that generates memes or something, and I use it to maybe download a meme. And if I can't use it right now, do my users expect, the uptime of 5 nines? Do they expect me to have less than 6 minutes of downtime in a year? Do they expect me to be able to bulk batch process 1 million memes at a second? Is that something that the user expects, or can we kind of maybe we don't need to be that available? Does this service tie directly to revenue? A meme service, like I was describing, probably doesn't tie much to my revenue, and there's probably not a lot of customers who, I would say memes are directly tied to the revenue. There probably are some, but definitely not like email. If email is down and people can't send emails, this could potentially cause them to become in breach of their agreements where, they had to respond to requests within a certain amount of time and they didn't, and now they're in trouble, and that could negatively impact the revenue of the customers. Are these services free or are they paid? That's kind of a big one. A lot of people with free services tend to have a little bit lesser on, okay, it's a free service. If you're paying me, I'm obligated, but if it's free and it's maybe it's my side project, maybe I don't need that much availability. What does the competition look like? If I'm the only one in the market and I'm bad, I'm still the only one in the market. But if there's a lot of competition and a lot of people don't, me having one outage is the difference between me and the competition, or people moving, or the competition is outperforming me in requests per second or another valuable metric. and I'm worried about losing customers, then maybe I need to adjust my availability to meet my target, meet my my competition. And what does my target audience look like? Consumers or enterprises? Consumer, it's a big difference. If you've ever worked in a sales engineering org or you've sold enterprise software, the difference between consumers and enterprises is in how they consume software and what they expect of software is really different. Consumers are a lot more forgiving and don't have these very large contracts that would say, if I can't access Google for more than 3 minutes a day, you're gonna pay me $50,000 because you're in breach of this contract. Whereas with enterprises, they could have something along those lines where you have a large scale software operation that you've sold them a service, and if that service goes down for more than the agreed amount of time, they may be entitled to getting a slight rebate because the service is down. So knowing your availability, really, you have to answer a lot of questions about your services and kind of figure out how available you need to be. And then a lot of questions that I get whenever I usually talk about availability and such are, what about the nines? And every DevOps, SRE, sales engineer, used car salesman, the lady who cooks bread at my supermarket, everybody talks about the nines. Not really, but it's the big thing that you hear a lot when you talk with DevOps and SRE folk. And it's basically when your uptime is measured, it's usually measured about as the number of nines in your percentage. So 99%, which is 2 nines, 99.9%, they call 3 nines, 99.99%, and then it just keeps going on and on and on and on. And what this basically amounts to is how much downtime can you actually have in a year? So like say 90% would be 1 9, and that you are allowed 36 and a half days per year where your service could be potentially unavailable, or, in an hour, 6 minutes, every hour, 6 minutes, you could be down and not have it available. And then it just goes up from there. And really and truly, you really do start to see like law of diminishing returns as you go, I guess, as you get more nines in your thing. So, with 99.5 is 2.5 nines. So you get 1.83 days of outages. That's a long time, actually. Like if you think about it, like if you think of almost 48 hours worth of a website being down, imagine if throughout the entire year, Google was down for basically almost 2 days. It would be really weird. I do know, because I read it in the SRE book, is that Google Compute, the GCP platform, actually has a SLAs nines time of 99.5. So they can be down for 4.5 hours, a little bit less than 4.5 hours every year. But yeah, so if you ever hear anybody talking about the nines, it's a very common thing that I hear about. It took until someone explained it to me, I had no idea what they were talking about. It's about the amount of uptime or about the amount of how much availability you are promising. So do I need another 9? Say I'm at 99.9. Let's go back to that chart real quick. I'm at 99.9, and yeah, that's 8.75 hours per year that I can be down. But do I need to go up to 99.4 nines to where I'm only down for 52.6 minutes? Well, the question you have to ask yourself, because a lot of this is where site reliability engineers and DevOps people can fall into the trap of over optimizing. So you need to ask yourself, what will the increase in revenue be? Does this extra revenue offset the cost of engineering? So if I increase my availability, one, will my customers even notice? Are there customers that I'm losing because I'm not a certain amount of availability? There actually are enterprise customers that do demand a certain amount of uptime, or they will not purchase from you. So that could be a thing. Does this extra revenue offset the cost of engineering? Because getting from 3 nines, the more nines you get, it becomes exponentially more difficult to ensure that the system doesn't crash, because you're becoming more vigorous with your change logs, with your change control systems, with what you allow to roll out, all your updates and stuff. It's actually relatively tough, because you don't want to breach it, and you have to be. The more nines you add, basically, the more careful you get. The more process has to be in place, the more automation has to be in place to do a lot of this. It's not that it's a bad thing, but it's not a trivial task in engineering land. So if the proposed improvement is from 99.9 from 3 nines to 4 nines, the proposed increase in availability has gone up less than 0.09%. So like less than 0.1%. I hope my math is right there. So say my service brings in $1 million of revenue a year, just an arbitrary number because 1 million is easy to divide into percentages. The value of the improved availability from going from 3 nines to 4 nines is just the amount of the service revenue multiplied by the improved availability. So by going from 3 nines to 4 nines, which is not an easy task to do, really only has a value of about $900. Which is actually really low. Like that, like all in all, that's all the budget I'm allowed to spend to get from this thing. If you actually, practice this. A lot of engineers or a lot of companies won't really do this math, but it's a good metric to kind of go over. If you can build it out, the extra 9 for less than or equal to $900, then it's worth it. Otherwise, you're going to spend more money than you're making trying to get it to build it out. And if we just do a quick little piece of math, an SRE at roughly $120,000 a year, which is I would say that's that's a maybe SE2, SE3, or individual contributor 2 or 3 base salary for site reliability engineers, makes roughly $57 an hour if you assume that they work 8 hours a week, 5 days a week for 52 days a year, or 52 weeks a year. If you actually factor in vacation stuff, they make a lot more. So a $900 budget would only really give you 15 and a half hours that you could spend trying to get that 4th 9 before you would run out of money, and it would no longer be worth the benefit to do it. So before you over optimize and before you really think about it, I would just say make sure you go over this, because if your customers are happy with 3 nines, getting to a 4th 9 isn't going to make them any happier. And actually, we're going to go over that later. It's going to make them have a perception about how your service works. And then if you actually drop below it, even though it's not what you stated, it'll cause problems. So I think that's later in my slide deck. We'll go over that in a minute. So one of the tools that we use to measure everything are what are known as the service level, or the SL stars, SLIs, SLAs, SLOs, or SLD'OHs is the title of this talk was. So, when I first started as an SRE, I was like, I don't know these acronyms. The computer science industry, I definitely, I had no idea. What is this? So SL stands for service level. Indicators, service level indicators, an easy way to think about these are the metrics that matter. So how many requests per second, what the latency is, how many successful requests, maybe how many failed gRPC calls were made, how many hits to the database, what the latency from the database is, how long that query is taking. These are the indicators. These are the metrics that we actually want to measure. Service level objectives are the ranges where these metrics should be. So the indicators you can almost see as raw data. There's no rules. There's nothing around them. It's just the data. The objectives are, okay, I want to make sure that I have less than 3% failure rate on my API at all times. That's going to be my service level objective. So if I go above that, I am now in breach, which is a hint that there's something wrong, either wrong in the system, or it means that there was, well, I guess it is wrong regardless, but it could be an outage, or it could be maybe a bad code push or something. Not all breach of service level things are the cause of outages. Sometimes it's the result of improperly optimized code, or just maybe latency because we put it's calling the wrong database, that database that's in a different availability zone on a different side of the world than we are, and maybe we didn't notice that. So objectives are what the ranges of the metric should be, and the agreements are how we'll react if we do not maintain a promise to you. So if something goes wrong, what are we going to do about it? So service level indicators. So a service level indicator, as defined by the SRE book, is a carefully defined quantitative measure of some aspect of the level of service that is provided. So it's like this check engine light, the tape must have fallen off. So some examples of these would be request latency, the error rate, your system throughput. All of these quantifiable, measurable things are service level indicators. Service level objectives are a target value or range of values for a service level that is measured by an SLI. So basically, it's the ranges that we accept, that we know, and if we go outside of the bounds, either too high or too low, we know that there's either an issue or there's a problem that we do need to investigate. So then there's this little meme. The lower bound, it's basically, like an inequalities equation. The lower bound, the less than or equal to the SLI, which is less than or equal to the upper bound. So you want to be able to define good objectives and know and be able to monitor them. And we're going to go over that in a little bit. So SLAs, an explicit or implicit contract with your users that includes consequences of meeting or missing this SLOs. And in reality, the best way to talk about them is the Padlin meme. So if you increase the latency, that's a Padlin. If you're dropping the packets, that's a Padlin. And then it just goes on from there. So SLAs are what happens whenever you breach these issues, whenever you have made a mistake, or whenever you are outside of the contract bounds of what you said you would provide to your customers. So how do we define SLIs? You need to figure out what you and your users care about. So the user-facing systems usually care about availability, latency, and throughput. Could we respond to a request that we were given? How long did it take, and how many requests could it handle? So again, if I'm doing a meme generation website, did I respond to the user in an appropriate way? Did the user have to sit there for 30 seconds while I was doing this? And if they do have to sit there for 30 seconds, were they aware that was going to be the case? Were they expecting instant feedback, or were they, I'm rendering images. Is it possible that was going to take a long time and we informed them of this? And then how many requests could we handle? Do the users care if my meme site can handle 1 million memes per second? Well, maybe it does if there's 1 million users trying to use that site simultaneously. But if not, if we can observe the traffic and we get maybe 300 hits an hour, or maybe, heck, even 300 hits a minute, then we don't need to be able to respond to it. We need to process 1 million a minute. The users are totally happy. We should maybe aim a little bit above it, so that way if we do grow, we can expand with it. But if the user doesn't expect it, don't give it to them. Storage systems usually care about latency, availability, and accuracy. How long does it take to perform this disk I/O operation? How long does it take for me to save my data? Can I access my data when I need it? Is my data still correct? Imagine if you uploaded something to Google Drive and then you downloaded it and the document was completely different because some bits flipped and they didn't do any sort of error checking and stuff was busted. Accuracy on storage systems is extremely, important. It's actually, I wish I remembered the file system, but whenever they were building UFS and stuff, there was another file system around that time that got a reputation for being a bad file system that curdled and then would corrupt user data. And even after they repaired it, it still has that reputation of corrupting user data. So if your application gets this perception, this notion of it that, it's going to do X, Y, and Z, that's really difficult to overcome. So accuracy in storage systems, very valuable. So how do we define SLOs? Keep it simple. The more complicated you make your SLOs, the more difficult they are to respond to. Also, too many data points can obscure changes in performance. So if you have 80, 90, 1,000, whatever amount works for you, SLOs, and then you're having to go through all this data, and some of them change and some of them don't and stuff, it can make it really difficult to easily be able to sniff out and detect where the problem came out from, which actually kind of sounds counterintuitive when you think about it, but it's true. Measure the things that are important to you, keep it simple, and you should and with less things to have to observe, you should hopefully be able to find it quicker. Avoid absolutes. We will be up 100% of the time. No, it's a bad SLO to have. 100% of the time is unrealistic. We will do this, we will do that. Just absolutes are never good. There's going to be wiggle room. There's going to be range. Someone's going to have a bad day and push bad code, and that's fine. That happens. That's the nature of being a software engineer. We don't always write everything perfectly the first time. Code doesn't always get pushed correctly. Sometimes there's gaps in our testing. But you don't want to have absolutes when you're dealing with this stuff. Be cautious when picking a target based on the current performance. So you want to avoid getting locked into supporting something that could require Herculean efforts to support in the future. Just because you're, maybe you just started, you're a brand new app and you can handle 1 million requests a minute. Well, as you add more features, as you add more complexity to the code, those requests are likely to slow down, and you have to try to avoid, if you defined yourself based on the earlier one, and now you've slowed down and there's nothing you can do except pull out features because code just doesn't run that fast, you've kind of locked yourself into it, or you're going to have to spend all of this extra effort to try to bring yourself back up to an old standard that you set for yourself, because it's very difficult to change service level agreements with users. I mean, they sign contracts. Enterprise customers sign contracts. They expect something, and you're not going to be, whenever the salespeople go to resell the contract or something, if you've said that you've lowered your availability, that could potentially cause a problem. If you have no other metrics, it's a good place to start. So I get it. Like, well, I don't know what I'm doing. Like, how do I even start with this? Totally get it. It's totally fine. Start there. Leave yourself some headroom at the top to where your performance could get a little bit worse, just to save yourself some headache down the road. Limit the number of SLOs. Choose enough SLOs to cover your system and allow you to win a conversation about prioritizing. So if you're in a meeting and you're talking about all of these different things that need to get done and all of that, and some of them are around, this will keep the SLO, this will make the SLO better, or this could potentially damage it. This can help you win. SLOs can help you win meetings, because you're like, no, we have this agreement. We have to honor this agreement, and we can't really, we can't go away from that. If you can't win an argument with an SLO, it probably is unnecessary. So that's a good litmus test. Is this SLO necessary? If I can't use it to win an argument with the product manager that, no, we need to spend more time repairing this thing than we do adding this new feature, then maybe it's not the right one. Again, nothing in here is black and white. There's a lot of gray. There's a lot of flexibility in all of this, which I think I literally just said. Note that some attributes, such as user satisfaction, aren't covered by SLOs. So if your user is happy, and they like what's going on, there's no SLO for user happiness. But that's still something that has to be, addressed. It has to be taken care of. So again, there's a lot of gray area here. Again, find what works best for you. Perfection can wait. It is easier to add 9s than it is to take away 9s. If you're getting no complaints about the speed of your service at 3 9s or 2 9s or a 9.5, then don't worry about it. If you're trying to sell to people that need that kind of performance, or if you start running into that, because trust me, if people are unhappy with it, they will let you know in some way. They will send you a support ticket. They will just blast you on Twitter. They will do something to let you know, hey, can your availability go up? And then once you've gotten enough of those, kind of measure, hey, we're becoming a more, high-end requested service. Maybe we should actually up the amount of 9s that we have. And then you can discuss it then. How do we define SLAs? SLIs are usually defined at a company level between business and legal, and involves reparations to customers. So if a company doesn't keep up with a certain SLA, there could be litigation. They could be having to deal with it. It's part of the contract. They're in breach of contract. It could become an issue. So as engineers, you may be in the conversation, but about what are some good ideas, but you're not going to be defining these yourself. This is really, you might help with the draft, you might consult, but this really is going to be done between business and legal. If your customers are internal developers, however, then it might be within your team's ability to define SLAs. The team that I worked on provided a PAS for all of the developers inside of HomeAway. All applications that were part of that website were deployed internally to us. So we had our own SLOs, SLIs, and SLAs, and we had SLAs because our platform actually did bill back. So if you put your app on our platform and your team's budget would be billed for the amount of resources that you were using, and we had a billing API for that. If we were to break that and go outside of the SLA of the availability for a certain amount of time, we would actually credit those customers back, and these customers are internal developers of the company with that, and then that would come out of our budget because we failed to maintain an SLA. Okay, so I imagine that a lot of people's heads with this are probably doing this, because this is a lot, and I will definitely say that this is definitely a lot of stuff. It can be overwhelming, and I get that. So what should you actually care about? What should you actually take notes on? Maybe I'm sorry. The whole point of this talk was so I could laugh at my own jokes, and I'm just laughing at all of these Simpsons memes. So if it hasn't entertained you, it at least entertained me, and then that's worth the value of it. So SLIs are things that can be monitored and measures. SLOs are ranges that are acceptable. These are things that it would be good for you to actually watch. SLOs set expectations for your services. So these inside your team, this will be up for this amount of time. This will have this kind of error rate, this kind of latency. These are the expectations that your team talks about. And when you talk about your product with other teams, this is how you're if another team wants to use your API, you can bring these to them. This is the error rate that we expect. These are the agreements that we have. Monitor and measure your system's SLIs. And so you need to be able to monitor them and know what's going on, so that way you can actually know when they've gone outside of the range of the SLO. Compare the SLIs to your SLOs. If action needs to be taken, take it. Determine what action needs to be taken to meet a target. Creating runbooks, automation tasks are really good for this. So just because you're in breach doesn't always mean that something needs to be done code-wise. If, say, US East 1 went down as an Amazon cluster, and I'm now having issues with this. Yes, technically I am in breach, but I am in breach because someone whose SLAs that I rely on are in breach. So we would escalate that up. We would communicate down to the developers what was going on, but essentially this SLA breakage is not my fault. This is the fault of the service provider above us, and you're going to kind of see this. So we were paths that provided stuff. We had SLAs. If you're an API team creating something and you own an endpoint, you could have your own set of structure around SLIs, SLOs, and SLAs. You have an agreement of the people of your API, whether it's external facing customers or internal facing customers, of what the agreements are. Now, not all agreements end in paddlings. Okay. Sometimes, maybe it ends in a root cause analysis meeting. Maybe it ends in a meeting where another director is very upset with you because you took down part of their site, because you took part of theirs down internally. They don't always have to require necessarily reparations. If I was on a team that I built an API and it broke, and somebody else was depending on it and I'm fixing it, I don't have to buy them lunch the next day. I mean, it might be a nice gesture. You might want to try to do that. Maybe take them out for a beer. Their heart rate probably went up when PagerDuty went out, so they probably need to de-stress a little bit. But I don't think it's not always going to be monetary reparations and stuff. Sometimes it's just apologies. So take action when needed. Always and preemptive action is always better than, reactionary action. If you see something starting to go south, take action and deal with it, because the likelihood is, or at least, and that action can be maybe monitoring it, maybe paying a little bit closer attention to it. Maybe you have a top level dashboard, maybe drilling in, SSHing into some of the nodes, maybe checking some of the logs, just seeing what's going on, and take actions as necessary. So a couple of tips regarding all of this. Have internal SLOs to your team that are higher than your external SLOs. So if I say that I'm going to provide you with 3 nines, internally, I might say that to the team, we have 3.5 nines. We want to stay above our SLO. So that way, even if we do something where it causes a gap, hopefully, or it causes a decrease in our availability, the decrease in the availability that we created was in our artificial barrier that we created for ourselves, and it doesn't trigger an incident. So definitely try to make it higher for yourself than you would for your external facing ones. Users build. This is just software engineering. How software engineers build. They build based on the service you provide rather than what you say. So if I say it has a reliability of 50%, and then you as a developer are using this service and you think, oh, it's got a reliability of 100% because it's never down. Maybe I was lowballing it. Maybe I was drunk when I wrote that message. Who knows? Customers will become accustomed to that. And yes, if you end up eventually degrading down that far, yes, you are not in breach of the agreement, but you are still open to ridicule, and people may potentially leave your platform because of that. So you have to be wary of that. You can avoid this by rate limiting requests, by designing the system to produce similar performance over light and heavy loads, or you can actually do planned outages. You can plan an outage and take the service down for either a maintenance that you want to do, or just to stay within your range so customers don't become too dependent on it. I know that sounds really sketch and really shady, but Google actually does this. They have a process called Chubby that introduces planned outages because they were overly available. They were too available, and people became to depend on them for what they actually were putting out rather than what they said they were, and people get upset about it. So now every now and then somebody just kicks the server, unplugs the Ethernet cable for a little bit. Not really, that's not how Google works, but it kind of, just do that. It's weird. It feels weird. I've actually never performed a planned outage I perform maintenance outages. I've never performed a planned outage for the sake of remaining within inside of these gaps. So it's pretty interesting. But yeah, it seems a little bit weird to me, but it seems weird to everyone. Breaches of agreement are going to happen. Okay. Like there's going to be a bad day. We work in technology with magic rocks that we have enchanted to pass electricity over them, and they get cranky sometimes. And it's going to happen. Just breathe and do your best to get the system back online. Don't worry about, get it back online, get it going. There will be time for analysis. There will be time for figuring out what's going on. But at the end of the day, just try to make it. Just try to make it, and don't panic. It's scary. My first time on call was terrifying, especially when you work for a company and they make a habit of telling you that this is a $1 billion company, this is a multi-billion-dollar company, and the entire company rests on your platform. And it was me and 4 other engineers. And if the platform goes down, which in the entire time that I was there, we had one serious outage that caused major problems. The failover region still worked, but we poisoned the main region, and that was a weird situation. But just don't worry about it. It's scary. You'll get through it. There is no room for blame inside of an SRE org. All postmortems should be blameless. You're not going to foster good health. You're not going to foster good team camaraderie. You're not going to foster trust by, it's his fault. He pushed the change. Why did he do that? Blameless postmortems are a thing. There's actually a really good talk by Chris Wilcox, I believe is his name, who does it who's done a talk at Pythons about Google's blameless postmortems. If you haven't seen them, you should definitely look them up. I think I know he gave it at Pi Ohio and at Pi Gotham. So definitely look those up. But you can't be a jerk when you're doing all this stuff. You got to be blameless. Take it as an opportunity to learn. And if somebody made a mistake because they didn't know something, and this is just my opinion on this one, if you have a junior teammate that makes a mistake and they do something wrong and it wasn't documented, then that falls on the senior members teams for not documenting and not teaching correctly. Unfortunately, while a lot of the tech space has gotten better, when you deal with older curmudgeonly sysadmins, sometimes they become they're less likely to want to teach, less likely to be friendly, and you have to foster good team growth. So, and that is pretty much it. There is the Simpsons credits, and we are good.
Awesome. Thanks so much, Mason. Can we get a round of applause for Mason in the chat? There's a lot of great comments about how much they've loved your Simpsons memes. So it is time for Q&A. We'll just take a couple of questions. If you do have questions, please ask them in the chat. We'll take a couple now, and then Mason, I'm sure you can provide your contact information and we can get to more later.
Definitely.
So first question I see is, can you see the screen? So it's how do SREs guarantee objectives, given that some of the problems that you encounter will be problems that you've never seen before?
So that's a great question, actually. So if it's a problem that you've never seen before, this is why you don't overpromise. You give yourself, and I didn't have time to go into it today, and there is something of a concept of an error budget. And if you read the Google SRE book, they talk about this in some detail about you give yourself a budget of unknown unknowns. You don't know what's going to break. You don't know what's going to go wrong. So you give yourself this time. So when that does happen, you can take it out of that. And that's against or that's also a part of the not over promising. You don't need to be 6 nines and have 2 seconds of downtime a year. If you do that, when you have an unknown, you're screwed. You're going to breach agreement and it's going to be a problem. So yeah, definitely. If you have a chance, check out that book. It's on error budgets, but this is why you don't overpromise on availability.
Awesome. I guess I just have one more question before we're just gonna wrap up and take a break before the next speaker. Going back to our question of the night, what is your favorite Python library?
Oh my goodness. That's a fun one. It's actually weird. My favorite Python library is in the standard library, and it's argparse. I think argparse is one of the best command line tool building libraries that I've ever seen. And it's really awesome. And I love it. Like, as someone who's dealt with stuff in sys and C and stuff, it's not. And I saw one question pop up in the chat that I'm going to answer really quickly because it's a very good one. Are SREs underpaid and underappreciated? No and yes. Our SREs get paid in a lot of money. Are they underappreciated? You only notice the SRE when the damn thing is broken. Like, nobody knows or cares about me when it's working, but when it's broken, I hear about it. So yes, are they underpaid? No, it's actually very lucrative if you can get into that. I enjoyed it for a while, but are they underappreciated? Completely, because again, you only exist when stuff is broken to the rest of the company anyway.
Awesome. Thanks so much, Mason. There's a couple more questions, but if you don't mind just taking it offline to the chat, that would be awesome.
Definitely. I will hop in the chat real quick on the YouTubes and I will ask them. So I will do that. Thanks, Ollie.
Thanks so much, Mason. Can we give Mason another round of applause? So we're going to take a couple of minutes break and then we'll have Dean start up. So please hold on and we'll be right back. Hey everybody, we are back. How many people enjoyed that talk? If you did enjoy that talk, please go down below and hit that like button. It really helps us out. Actually, I really don't know if it helps us out, but it sounds like something they always say on the YouTubes. So next up, we have Dean Wampler. Dean, thank you so much for joining us. We're really excited to have you.
Hi, Ali. Glad to be here.
Can you tell us a little bit about yourself?
Yeah, sure. I'm also in Chicago. I actually work for a Berkeley company at the moment, Anyscale, which is the company developing Ray. But yeah, I've been here about 15 years. I actually only recently joined the Python community. I've been in the JVM world for a long time doing middleware stuff there, but kind of got into Python because of machine learning and AI and all that stuff.
That has been working in the JVM and is new to Python. How are you enjoying our community?
I enjoy it a lot. I mean, it's just an incredibly rich, diverse community, right? Not only in people, but just tools and so forth. It's kind of crazy that this really old scripting language is still like, the dominant programming language. Maybe after JavaScript, I forget which is number one. Who cares really? But yeah, it shows you how malleable and adaptable it is.
Yeah, for sure. It's awesome to see those rankings keep growing. The number of questions on Stack Overflow feels like doubles every few months about Python.
Yeah.
Also, you are working as a developer advocate at Anyscale. Can you sort of just talk about what y'all have been doing at the company to keep building your community, but in a virtual way?
Yeah, Ray, which I'm going to talk about in a minute, is relatively new. It's not as well known, so we talk about this a lot because we obviously want to build out the community. But a lot of it is just building better training materials, documentation, doing talks like this, talking with the users of Ray, and finding out what works for them and what doesn't. So it's very much an organic process. There hasn't been anything that just suddenly we jumped or whatever. We're still looking for that big hit. Maybe if I don't know, some celebrity endorses us, then we'll be golden. But until then, we'll do it the old-fashioned way.
Well, I guess we need to find more influencers in the developer relations space.
That's right.
Also,
yeah.
cool. So, are you ready to go? Can we
I
get your
am.
screen shared?
Sure. I'll go ahead and share it here. And grab the window if I find the right one. I think this is it. Okay. Yeah. And I'm going to go full screen. So hopefully you can see this. Can everyone see this okay?
Yeah, it looks like you are all ready to go full screen.
All right, good. Well, thanks so much, everyone. I've been wanting to do a talk for you for a while. Like I say, I've been in the Python community relatively recently, or joined it relatively recently, but been in the Chicago meetup space for a long time. Like if you go to the GoTo conference, or if you happen to go to the Scala conference, or some of the big data, or Scala meetups rather, and some of the big data events. So I'll have most of these links at the end. But basically, Anyscale is the company that was spun out of Berkeley to develop Ray, which was a research project that I'll describe in this talk and why you might be interested in it. There's a couple of big trends going on right now that kind of really were the inspiration for Ray. One is this interesting picture that the size of neural networks, is what this is really plotting, have grown 35 times every 18 months. This is a log plot. And for comparison, Moore's law is famously 2x every 18 months. So you can do the math. We're obviously outstripping the ability of our hardware to keep up. Of course, that's been a general rule for forever in computing. But what it really means is we need to go distributed if we're going to meet the compute requirements we have. And of course, as we were just discussing, Python is once again on a rocket ship of adoption, driven in large part by the kind of insane interest really in ML, AI, and general data science. And it's really proven to be a great language for all of this stuff. And I think the reason Python is so successful is it's a very approachable language for people who are more interested in focusing on the problems that they're trying to solve and less on sort of language theory and that kind of stuff. And for me, it's interesting to compare the two because I do come from the Scala community, which is a much more sophisticated language, statically typed and all that. And I can appreciate the virtues of both for their different strengths and weaknesses. But anyway, what it shows is that we just have to keep thinking about how to do distributed Python, not just distributed over the cores and our CPUs, for which we do have a lot of good libraries, but going beyond the boundary of the machine to a cluster and make it as easy and approachable as possible. And that's really the vision that Ray has. So this is sort of a typical group of things that you have to do in the machine learning world. And if you're not doing machine learning or anything like that, I'm actually going to talk a little bit about microservices towards the end. But just to give you a flavor for kind of the compute problems that arose. In a typical data science world, featurization is about figuring out what characteristics of my data are actually useful for analysis or predicting future behavior. A lot of what we do now is done in the context of stream processing, hyperparameter tuning. I'll explain what that is in a minute. Model training you probably heard about, and simulation, like if you're doing so-called reinforcement learning, which I'll also describe briefly, you often are running like a game simulator or a robot simulator, something like that, to design a thing that can navigate through that environment in the most effective way. And once you've built this model, then you have to serve it. And all of these things typically require distributed systems because of the scale of the problem. And you can see all these icons for popular tools that are focused on, part of the space in one sense or another. The vision of Ray is that, maybe we can build a common framework that can sit underneath all of these kinds of problem areas, something that's relatively approachable. It's currently targeted towards Python, but it's actually designed in such a way that we can add support for other language APIs. And for example, Java is probably going to be the first one we support. And then on top of that, what actually most people will use will be libraries for training, hyperparameter tuning, and so forth. If you're a regular Python developer, like writing web services or whatever, then you might actually use Ray itself. So what is it like to use Ray? Well, one of the things that we tried to do is make it as intuitive and concise as possible and leverage familiar ideas. So we're all used to writing functions to do particular kinds of work, like these two on the left, where I'm going to have some function that constructs a NumPy array in some way, returns it, and then another function that adds it. Not a terribly exciting example, but simple enough that we can focus on what Ray is doing. To make these things Rayified, if you will, you add this annotation, ray.remote, and what this does is it turns them into what we call tasks. We use that term because now these things can be distributed across a collection of workers across your cluster, and then do the work of the computation required here. Do it asynchronously, do it in parallel as a result, and then you can gather the results when you're done. I should say, for completeness, if you tried to type this in and run it, you'd need to do or add the code on the right, which does the imports and initializes Ray. Maybe I should have added you do pip install Ray before all of this, of course. Okay, so how do you actually use these tasks once you've defined them? Well, there's actually a change in the way you invoke them. Instead of saying make array and then argument list, it would be make array.remote argument list. Now, Python's a very malleable language. We could have designed Ray so that you didn't have to change the way you call these now tasks. The reason we think it's a good idea, though, to leave this in place is so that just by reading the code, it's sort of self-documenting. You know that this is a remote task invocation as opposed to a normal synchronous function call. And what it's actually returning is the ID for a future. It'll be, again, this is an asynchronous task. It could be running on any machine in your cluster, but this ID will give you a hook for retrieving the value later on once it's done. So we could call it again and get another ID. And then we could call this add arrays task to actually add the two arrays together. And that returns yet another ID that we can then get the final result from. There's a couple of interesting things going on here, though, that are designed to make it as easy to use as possible. The first is that we actually have a dependency between these tasks. We can't execute add arrays until the other two are done, but you don't have to worry about that. Ray detects these dependencies and automatically sequences them for you. So even though you fired off these 3 asynchronous tasks, the last one, add arrays, will not be scheduled and executed until the other two are done and the results are available. And the other thing that this does automatically for you is, notice that I pass those IDs to add arrays rather than passing NumPy arrays. I didn't have to pull out the objects and pass them in the correct way. Ray handles that automatically for me. So that just a couple of things where with relatively simple modifications to your Python code, you can get this asynchronous execution. And then to actually get the value when you're done, you make this blocking call that will wait until ID3 is can actually return the object that it's referring to somewhere in the cluster. Now, one thing we haven't talked about yet is what about distributed state? This is one of the biggest challenges writing distributed systems as you start having your state spread all over the cluster, and it can be hard to keep track of, hard to manage. So once again, we try to leverage a familiar idea, which is classes. These are an encapsulation of state and methods to operate on them in hopefully some intuitive way. So this is a simple example of a class that just does a count. Every time you call increment, it increments an internal state value, and then you can retrieve it to see what's going on. There's actually a flaw in this example. I just noticed, I've done this talk several times. When you use Ray, you actually have to add a getter method to retrieve the value. You can't just call self.value to get it. But anyway, conceptually, it's very much the same. Anyway, so what are we going to do? We add the annotation again, and now we turn this into an actor. Now, if you haven't heard of the actor model of concurrency, it's really a very beautiful, simple idea. It's the notion that each of these actor instances are like autonomous agents. I'm going to send them messages, in this case, increment, to do work, and the actor system will guarantee that it's done in a thread-safe way. So if this thing's being hit from all over the cluster, you won't get like invalid state corruption because you didn't handle thread safety. The actor system handles this for you. It's been used in a lot of systems. Those of you that happen to know about Erlang, for example, or maybe Akka in the JVM world, will know that those are examples of actor systems. So that's where the word comes from. And you call it pretty much the same way. You use this remote annotation on the constructor, on the method calls, and then you can also retrieve the values when they're done. Notice you can pass a list of IDs to ray.get if you want to. You don't have to just do it one at a time. Okay, let's take a look behind the scenes a little bit to see what's actually going on. I always love to do this when I'm encountering a new system so that I really have more of a sense of what's going on and more empathy for the machine, if you will. So let's imagine we have a 3-node cluster, and on each of these nodes are these processes that are running that I'm going to describe. And what we're going to see is how this particular scenario of tasks might actually be executed. So first, let's imagine that the driver for this program, this regular Python program, is running on node 1. It will send these tasks to the local scheduler on that node. This is a array task that's running in the background. And it will return the IDs immediately because that's just firing off these asynchronous processes, so I can go on and do other stuff while these things are running in the background. And this global control store is kind of like where all the metadata is kept so that the Ray system knows where everything is running and so forth. So suppose the local scheduler decides I've got space on one of these local workers, so I'll schedule this one to run locally. But maybe it decides it needs to schedule the other one on another worker. So I kind of cut a few corners here. It actually communicates to the other scheduler that then schedules it on the worker. Now, when these two finish, they're actually going to write their objects to this object store. This is a in memory. It's actually shared memory, as we'll see in a second. It basically leverages Pandas Plasma object store, if you're familiar with that. Now, as I said before, because these tasks have finished, I can now schedule add arrays. Let's suppose I schedule it on the same node. Now, it doesn't need to copy object 1 into its local memory space. It can actually just read it because it's in shared memory. So if object 1 were enormous, then that could be a big performance boost if we were doing this over and over again a lot of times. Now, object 2 obviously isn't on the same node, so we're going to have to copy that over, and now it can be read from, again, shared memory. And then when add arrays is finished, it writes its result back to object 3, and then we can call ray.get to fetch that object using ID 3, and we're basically done. So that's sort of what goes on when you run in a cluster. When you're actually running on your laptop, it's basically like node 1 by itself is running. It's a little bit lighter weight, but you're still basically running in a concurrent way, and you can actually get a lot of performance boost just by being able to spread the work over all of the cores in your laptop or workstation or whatever, even if you don't have a cluster. Okay, what about if you wanted to migrate to Ray? Maybe you've already written a lot of stuff in some of the traditional multiprocessing libraries like multiprocessing.pool or joblib or async. Well, it turns out we've actually implemented these in Ray as well, these APIs. And normally it's just a drop-in replacement where you just change the import statements. And what you actually get then is the ability to simply have these constructs scale over a cluster instead of being bounded by the node that they're running on. And I should mention, in all full disclosure, there is extra activity going on that Ray is doing because it's doing this distributed stuff. So in some cases, if you only need to be on a node, it won't necessarily be faster. It could even be a little slower because of the extra overhead that Ray has to have for all the work it's doing. We're aware of this. We're trying to get rid of this, so it's just a no-brainer to use these implementations. But that's one thing to think about if you were deciding whether or not to switch. And the overhead difference is not that big, but if you're really, really concerned about performance, you might be thinking about it. Oh, I guess I should have mentioned, there's a couple of blog posts at the bottom. I'll make these slides available that you can read more about how these APIs work. All right, let me talk a little bit about the libraries for machine learning, a couple of them that are built on Ray. I think most people who are using Ray will be essentially like most people using Python. They won't necessarily understand or have to understand the internals of Python. They're just using this abstraction on top. Similarly, a lot of people will use these machine learning libraries, never actually drop down to the Ray layer, but they'll of course be using Ray under the hood. So here's that graph again or chart, if you will, of features or things that you have to do in typical machine learning and data science environments. And these are 4 of the libraries that we've implemented using Ray. Ray SGD was actually just announced this week in a blog post on our website. Servit was recently announced as well, and we haven't even done an icon for it yet. But what I'm going to talk about are RLlib and Tune. So RLlib is for reinforcement learning. It's perhaps our most popular library. It's certainly the biggest, most sophisticated of our libraries. If you haven't heard of reinforcement learning, it's really, at least at a conceptual level, very simple. You have some agent working in an environment and it wants to learn the best way to navigate through that environment to maximize its reward, whether it's playing a game or learning to walk, like the little weird icon with the robot on the bottom, or learning if it's a real robot and it needs to learn how to pick and place things. That's basically the idea. And the way you train these things is that you just have them do this exercise over and over and over again, and they learn what things seem to work better than others and eventually triangulate to what is hopefully an optimal solution. One of the most famous examples is the AlphaGo system that beat the world's best Go player. A few years before this happened, people assumed it would be a long, long time before machine learning systems got good enough to beat a system like Go, which has a huge state space. But they basically did it by using a neural network to help make decisions. They observed the board state. They decided where next to place the stones on the board. And in this case, the reward was either win or loss, 1 or 0. So you've probably heard about a lot of these applications of reinforcement learning, like training a robot to walk or training a car to avoid pedestrians or winning games. We are starting to see some interesting applications in industry outside of these. A couple of my favorites are on the left. There are a number of companies that are starting to look at process automation, like think about how a factory floor works or how something complex is assembled. How can we optimize these processes? How can we optimize like chemical control processes and so forth? Another interesting one is advertising and recommendations are kind of related. They're finding ways to use using reinforcement learning to improve the quality of these things and deal with the fact that they're often dealing with enormous state spaces. Like if you think of the classic way of doing recommendations, you have a massive set of customers and the things that they've rated, movies, let's say, and then you come along and you want a recommendation, so they try to find how you match. It's a giant matrix, linear algebra problem, and it's actually just too big when you're somebody like Netflix or whatever. So they're actually using RL to improve the quality of these things and get around some of the compute challenges of them. And then finance, of course. If you think about the stock market, it's a time-varying system, just like a lot of these other sort of games or systems we're talking about. It's also a candidate for RL. So what RLlib tries to do is, you have these applications on top. You have several sort of general big strategies you can follow, like do I have just a single agent in the environment, or collaborating agents? Are they structured hierarchically? Offline batch is kind of an interesting one that I think is up and coming. It's the case where, you know what, I can't run my chemical factory over and over again to train your silly system, but I can give you a massive set of logs for how it's behaved in the past. So maybe you can train something from that. So the offline batch is the idea. RLlib tries to give sort of a uniform API for all of these choices, and then it has a ton of algorithms that have been published under the hood. And of course, it's all running on Ray to get maximum scalability. So if we go back to this picture for just a second, RLlib was really kind of the genesis of Ray in a way. Reinforcement learning had some unique challenges that just weren't being addressed very well with the tools that were available to these guys at Berkeley at the time. And if you think about what's required on this problem, it's a very diverse set of compute kind of patterns, memory access patterns, and so forth. For example, the simulator, the game engine, or the robot simulator, or the factory floor simulator. These things are more like regular state machines or web service applications we're used to writing, which could be a lot different than some of the other things we're doing. The agent might also be very complex. It might have some big decisions to make or whatever. Then we've got our usual neural network stuff, the whole way that we train these things, the way that we manage the data, the whole parameter set, with some of these networks getting into the millions and billions of parameters, excuse me. So the point is, finally, that we have to not only handle all these different compute patterns, but we have to do it over and over and over again, because we're trying to learn the best approach. And train as we go. And that means we have to play these expensive processes over and over again. So we need things that do this as optimally and efficiently as possible, but also cover a wide range of compute requirements. And this was really the big inspiration for Ray, was this kind of flexibility, efficiency, and scalability was what drove the creation of Ray. This is a eye chart of some of the RL algorithms available in RLlib. If you've done any work with it already, you might recognize some of these terms. These are all links to the documentation. You can even play with this in Amazon SageMaker if you want. And now let's talk about Tune. This is the hyperparameter tuning system in Ray. So what's Tune all about? First of all, what is hyperparameter tuning? Well, here's the most trivial example I could think of. If you've ever done k-means clustering, which is, I've got a bunch of data and I want to find out where the clusters are, the first big decision is, what should k be? This illustration is from Wikipedia, and in this case, k is 3. I'm looking for 3 clusters. But maybe I should try 5 or 2 or something like this. So k is sort of the hyperparameter. And then when we actually find where these clusters are, the parameters that define those clusters are the parameters. So that's what we mean by hyperparameter tuning. It's what is the structure of the system that we're running, and then we actually train it to fit our data. And it really has become a problem when we've been dealing with these big neural networks. Every number you see on this picture is a hyperparameter. The size of these layers in the network, actually how many there are, whether they're max pooling or dense, all of this stuff are the sort of choices that we could make when we're deciding what model would actually fit our data best. And if you think about the combinatorial explosion you've got here, if you wanted to just naively try every combination, you could run forever. So a lot of the art of hyperparameter tuning is making intelligent guesses and using algorithms to try to prune off things that don't seem to be working that well, so that you don't waste resources doing training exercises on those, and you instead triangulate to a good solution. And then after you've got the good solution, namely the hyperparameters, the structure of your neural network, then you can actually train it with the data that you're in the full training regime. to actually create the model parameters that will then be used for scoring or recommendations or winning AlphaGo or whatever. It does matter. This is a case of just a simple example of 3 different runs where the blue one gives the best result, the pink one gives the worst, and it's all just a difference in their hyperparameters. So we want the best model. Resources are very expensive, especially if they're GPUs, and it's very time consuming to do training. So that's what Tune is trying to solve for us. And it effectively handles a lot of the parallel runs that are required to try different configurations. It's designed to be very easy to configure a training job or hyperparameter tuning job. You basically say what model you're training, a few parameters, the kind of optimization strategy to use when finding the optimal hyperparameters, and it's integrated with a lot of the popular frameworks. It's integrated with TensorBoard, so you can see what the parameters look like when you're done. And it's also very aware of the specific requirements for deep learning neural networks, such as scheduling to GPUs, integration with the popular frameworks, and so forth. All right, let me finish with a discussion that maybe would appeal maybe to those of you that don't care about machine learning, and that is, what about microservices? Now, first I should say microservices are getting sort of a backlash right now. You may have heard that Uber has announced they're going to macro services. Certainly people have drank the Kool-Aid a little too much on them, but you can strike the word micro if you want. What I'm going to describe is pretty much true for any sized services you care about. There's a couple of ways you could talk about microservices. One of their goals is to kind of separate responsibility. Like, one microservice might be doing DNS resolution, another one might be handling authentication, that kind of stuff. And one of the reasons you like to separate these things is you might need to manage them in a separate way. Some of these microservices might need a lot more instances than others because maybe they do expensive or hard calculations, or maybe they just hold or handle a lot more load. Sometimes you have to change them out more frequently because they might be evolving more rapidly. But the key point really here is that you've got to manage all these instances explicitly. And so it sort of raises a question, well, why do I have all these instances in the first place? Why are they necessary? Well, there's 2 reasons. One, of course, is that you might want multiple instances of something running for resiliency in case one of them fails. That's always important. And the other reason is just that you run into the boundaries of machines and you end up having to spin up another instance somewhere else. What if we could get rid of that? Well, that's the whole idea that here for how Ray could be really useful is that, and again, this is like, a vision more than a complete reality. There's a lot of details here that you'd have to get right. But you could go back to a little bit more of a model where you have one logical instance for each of these microservices, and then you use Ray to scale across the cluster. So effectively, you've created like one giant machine out of all of the nodes in your cluster. And that reduces the need to have explicit management of individual instances. We're thinking a lot about what this really means. I think this is a really good starting point that you could use today, but there's a lot more here that I think Ray can help us to make it a lot easier to build these highly distributed systems that are easy to manage, because it can do a lot of the sort of boilerplate for us behind the scenes. Let me mention one thing. How does this play with Kubernetes and stuff like that? Ray is very fine-grained. So really these actors just run as if they're inside nodes, whether they're physical machines or virtual machines or containers or whatever. It's just a different level of granularity, so it plays very well with a system like Kubernetes. In fact, there's tools inside the Ray distribution for working with Kubernetes. So in conclusion, we think it's a really new but already state-of-the-art tool for distributed computing, especially for Python developers. This is a bit of a tagline, but we think it's the shortest path from starting to work on your laptop and then going to the cloud. But it does let you run really complex, really big distributed tasks on large clusters with relatively simple coding constructs. Okay, here's some links for you. We do have some online events happening this summer, our so-called Ray Summit Connect, and then we're trying to do Ray Summit in November. It was supposed to be in May. For obvious reasons, it got pushed back. But check out anyscale.com/events for information. I'll tell you that there's going to be a lot more details posted next week. It's a bit sparse right now, but you can sign up for information. We are actually hiring. If you want to go to our jobs page, if you want to learn more about Ray, go to ray.io, and you can spam me at this email address. So I'll go out of full screen mode and take any questions anybody has.
Awesome. Thanks so much for that talk, Dean. So we do have a few questions. Folks, just going to add that to the screen. So folks are wondering what the relationship is between Ray and Modin. I don't. It's like the Pandas project.
Yeah, that's a good question. So Modin is a research project in Berkeley that's using Ray, and it's also using Dask to try to put a more faithful API of Pandas, and I'll explain what I mean by that in a second. Either on top of Ray or on top of Dask, and by more faithful, I mean I think all of the Panda-like implementations out there, like Dask, are usually a subset of the actual full Pandas API. I did mention Dask. Al, I don't know if that question came up. It usually does. What's the similarity or difference between the two?
Yeah, that question is also there.
Yeah, Dask is really great if you want to do distributed pandas, distributed NumPy arrays, that kind of sort of data analytics, traditional data analytics. We think Ray is better for more fine-grained, more general purpose distributed computing, like I described when I was talking about reinforcement learning. So they sort of compete in a way, like I said, and if Modin were a more mature project, then maybe they would compete more directly. But right now, I would go with Dask for what I just described, and go with Ray for the kind of general purpose compute.
Okay, awesome. There's also some questions around schedulers. So is this scheduler fault tolerant?
That's a very good question. You can basically set a flag now to have any actor that dies restarted. There isn't a whole lot there yet, though, in terms of like really high reliability, high availability sort of resilience. We're just getting started on building out the capabilities. Excuse me. For example, like I mentioned, I used to be in the Scala ecosystem, and there the big tool was Akka, and it had a very sophisticated model for declaratively specifying what to do to recover. We're still working on that in the Ray world. It's not quite there, but you can do some basic stuff already.
Okay, awesome. And the second question I see around schedulers is, how does the scheduler prioritize work? How do you make sure one worker doesn't take up too much CPU time?
Yeah, good question. I didn't show this, but you can actually, for those Ray remote annotations and also in the initialization of Ray when you start it up, you can specify resource constraints. So a common thing to do, not only constraints, but resource requirements. Like you could say this function or this task requires a GPU, and then Ray will make sure that it schedules on a node with a GPU. So it does have constraints that it will try to respect. One thing they've just been implementing, actually, this was a problem in the JVM forever, was making sure that they respect container restraints and not just node constraints. If those of you that have worked in the JVM at all may know that for a while Java would just blow past the constraints of a container and just look at what the node offered. Obviously not a good thing. That's the same sort of thing that we are working to ensure we obey.
Okay, great. And there's a question about the implementation. Before we get to that, if you do have questions, please ask them in the chat, and we will try to get to as many as we can. And so this question about implementation is, why not implement Ray as a backend to the standard library concurrent.futures, something like the thread pool executor or the process pool executor?
That's a really interesting question. We did do multiprocessing.pool, as I mentioned. I think it was a decision around how low in the granularity stack to go. I don't honestly know the answer to this question, why they didn't do it this way. And I'm not that familiar with the implementation, so there may be some of this in there already. But I will say, one of the things they've done recently is move a lot of the logic of Ray into the C++ core to make the Python API as thin as possible. And the main reason for that was to make it easier to support other languages. So if you decide you want like a Rust API on top of Ray, that there's less work to do.
And you were mentioning there were plans. What are the next languages on the horizon?
So there's actually a Java API that our biggest user, which happens to be Ant Financial in China. This is like the equivalent of Stripe over there, a spinoff of Alibaba. They actually implemented a Java API that is, it's actually in the code base, but it's considered experimental because we're still iterating on the API itself. Other than that, we've talked about C++. We've had some interest in Rust, which I'd love to see because I think Rust is kind of an interesting language. But Python is just so big, and we're mostly kind of focused on the machine learning world that Python is really going to be where most of our energy goes for a while.
So are there plans to go to R? Because I know it's used quite a bit in that same space as well.
We haven't had any requests that I'm aware of for R support. And I think it's probably just a matter of limited resources, and everyone in our team is just kind of a Pythonista and not that familiar with R.
Awesome. So we have Scott asking in the chat: does Ray tolerate dynamic scaling of a cluster? For example, adding or removing a node?
It does actually. In fact, one of the nice features they built into Tune is the ability to use spot instances, and it will recover. Going back to that question earlier, there is some sort of large granularity recovery that's built into some of the libraries that's now being moved into the core. I mentioned how expensive hyperparameter tuning can be. If you can use spot instances, that's obviously a big win because it's a lot cheaper. You'll just lose some of your work periodically. So it is actually Ray itself, and in some of the libraries in a more involved way are tolerant of adding and removing nodes in the cluster.
Awesome. I think that's all the questions in the chat. Well, we do have the question of the night. I'm sure you're going to say Ray, but besides Ray, what would you say your favorite Python library is?
Yeah, I do like the big machine learning libraries, like and the ones I've used the most are TensorFlow, PyTorch, and scikit-learn. Those are the ones that are really fun. Bottomless too. I have to say too, I've been using Bokeh a lot lately for graphs, and really enjoying that one as well.
Yeah, it adds a lot of interactivity with barely any work on your side. I love it.
Yeah.
Well, thanks so much for joining us today, Dean. Do you have any final things to say to our broadcast?
I do appreciate the opportunity to speak tonight, and I'm looking forward to when we can all get back together in meet space at some point. So.
Yeah, I can't wait either. We can't wait to have you actually give a talk in person. That would be awesome.
Looking forward to it.
Awesome. Well, thanks so much, Dean. We'll let you go.
All right. Thank you. See you guys.
All right, so that is it for Chippy's April main meeting. This was our PyCon preview night, and we did actually get one of the talks that was previewed at PyCon, so very excited about that. Let me pull up my calendar of events. Just give me 1 second. Oh, before we do that, we'll talk about the question of the night. What is everybody's favorite Python library? Let me go through some of the earlier comments. We got some love from Adam for Flask. People are also loving requests. That's Travex. Daniel's talking about NumPy. Of course, can't go wrong with the workhorse that's NumPy. Another shout out to Flask. One for pandas. Yeah, I see a lot more Flasks, though. That's awesome. I think my favorite would probably be PyTests. It's just amazing how much you can get accomplished without that much code. But yeah, talking about upcoming events. April 16th, which is next Thursday, we're going to have Python Project Night. if you join our Slack, there are links down below in the description. We're going to try to be doing it in a virtual way. We have organizers that are going to be in various rooms, and Chippy does have a few open source projects. Like our Slack bot is open source Flask application, and our website is a Django web application. There are a lot of open issues for both of those things, so please come on by. Or if you have a project of your own, we love to sort of work on it with you together. Where to find us? Our Slack links are down below. It's join Chippy slack.herokuapp.com. We are on Twitter. It's at Chicago Python. All this information and a lot more is going to be on our website, which is chippy.org. Thanks everybody for joining us. Look forward to seeing you again on YouTube in a couple of weeks. Take care.